Hey YouTube, today we're going to talk about how to use landmark attention to fine-tune your models for greater context. We'll start by talking about how to set up OobaBooga to correctly utilize landmark attention. Then we'll talk about how to actually fine-tune your models to landmark attention and the hyperparameters that affect it. And then how to actually execute the fine-tune, merge it together, and use it in OobaBooga. So let's get started. So we want to be able to run our model in something like OobaBooga, which now does support landmark attention. And to get it to properly support it, we just need to set a few parameters, specifically the repetition penalty, which we want to lower. Then we want to truncate the prompt length, and we want to set that to 8,192. And then we want to set our chat prompt size to also 8,192. And then we want to uncheck add the BOS token to the beginning of prompts. And then under model, we want to select trust remote code because the transformer library does not support this right out of the box. But now let's move on to getting our fine tuning set up. So the first thing we're going to do is navigate to this repository, which will be in the description below, but it's a fork of the official landmark attention repository that implements QLoRA, which means that we will be training the network quantized instead of as a 16 or 32-bit floating point network, which means that we should be able to train even 7 billion or 13 billion parameter models locally. So as long as you have enough VRAM, which should be 3080s, 3090s, or 4080s or 4090s, we should be able to train those 7 or 13 billion parameter models locally. So we're going to first check out this code and clone it down. So we're going to click on code. We're going to hit copy. We're going to go to our command line, and then we're just going to run git clone and clone the repository down. And then we're going to cd into there. And the first thing we're going to want to do is run conda create -n landmark, and that will create a conda environment for us. Now I already had this set up, so I'm going to overwrite my environment. And once that's been deleted, we're going to go, or once that's been set up, we're going to go ahead and run pip install -r requirements. And go ahead and let that install. Now, in my case, that was pretty quick because I already had it set up. But in your case, if you haven't ran these before, it will take a little while. But if you run into a problem with the transformer library saying that you don't have a method that it expects, just run pip uninstall transformers and then run pip install -r requirements again, and then that should resolve the issue. But now that we have it installed, let's go ahead and move on to actually fine-tuning a model. So before we start fine-tuning, let's go over the hyperparameters that you can set. The model name or path is the model that you plan to train. If you have your model locally, you just give it your local path. But if you wanted to pull something down from Hugging Face, you would do it just like you do with Ooba. The output directory is the local directory that you want to save your model to. The cache directory is where you want to save your Hugging Face training data. The per device train batch size is how much of the training set do you want your model to see at once. 4 is pretty small, and it will take a while for the network to actually learn the patterns, but higher values like 256 or 512 has a propensity to memorization. So you typically want to try sizes between 16 and 32 or maybe 64. The gradient accumulation steps, or how often do you want the gradients to go back into your LoRa's? There's not a lot of reason to change this, but you could try experimenting with 4 or 6 or 12. The learning rate is how quickly do you want the network to update its weights. This value probably shouldn't be updated, but for larger network sizes like 33 billion, you might try lowering the learning rate. The weight decay, I really don't recommend changing this. The logging steps are how often do you want things to log. I recommend with how long this takes with doing a step size of 1, just so you can make sure that your loss is going down like you expect it to. The warm-up ratio, this is kind of an odd concept. What it really says is how quickly do you want the whole training set to be used per step, and it increases it linearly as you go through epochs, and it just allows the model to kind of warm up to the training. The max step sizes are how many steps you want to take before completing your training. 200 is probably a good value to start with. We're not going to want to change these two. So BF16 and TF32, we don't want to train these or change these. The group length, group by length is we want to group things by similar lengths, and that does help here. And then the LoRa R is your LoRa dimensionality. So remember, we have low rank decompositions. So we have 32 being the inner dimension here, but for local, especially if you only have 16 gigs of RAM, I had to pull the LoRa dimension down pretty low to be able to train locally. But if you have 24 gigs of RAM, you probably could get away with 16 or maybe even 32. And then the LoRa alpha is how much influence do you want the LoRa to have on the network in totality. And a good rule is a quarter or a half of your LoRa dimension. Now let's get on to actually executing a fine tune. Once you have the model selected that you want to train and the hyperparameters that you feel are good, we can just run this command line, and it will be in the description below, but it's also in the repository, and it will just handle the rest. Now we can't really use custom data sets right now. We have the data set that's used to train by default, but that should be changed pretty soon, especially with structured data. The developer of this repository has talked about wanting to support structured training because it should help the model, especially models like Wizard or other instructional models, learn how to pay greater attention or pay the right attention to landmark tokens. But now if you'd like to try running this locally, I encourage it. I think it should work pretty well, especially on 3080s or 3090s or 4080s or 4090s. Though it will take a very long time because even on H100s, it takes 2 to 3 hours to train these, but it should take a few hours on local if it manages to complete running. So I would expect 10 to 14 hours in total on local hardware. But let's go ahead and execute this and see what you should expect to see. And you should see it starting to load the sharded checkpoints, and once it's done doing that, it will pull in the data set and then actually start the fine tuning process. And then once that's done, what we're going to want to do is actually merge the LoRa's into the network. So once that's done, we'll come back and do that. Once we're done fine tuning, all we have to do now is merge our LoRa's into our model. And that's because our LoRa's are attached to each layer. So if we try to run it in OobaBooga or any of the other chat apps, it won't run correctly. So all we have to do this is run the following command line, where we run python merge pef.py, our base model name or path, and we give it the model that we'd like to merge into. Our pef model path, this is exactly where our LoRa is saved to. And in my case, since I had it saved to LoRa, it's saved into this checkpoint and then the adapter model. And then the output directory that we want to save it to, we hit enter. Now, once this is done running, it will have merged the LoRa in, and we can run it in OobaBooga. And once it's done, we'll see how well it runs. So now that we have our model into OobaBooga, and you would just load it like you would any other model into OobaBooga, but now we can give it a test and see how well it performs. So what I have here is a bunch of text about engineering. And at the very beginning, I have a passcode that I want the model to remember. So let's see how well it does with this. And there are about 4,000 total tokens here. And this model typically only does 2,048. So let's see how well it performs. And it takes a little while for this to finish. But once it does, we should hopefully see that it remembered the password. And in this case, we'll see if it does. It should take just a few. There it goes. And it did. So the nice thing about this is we can give it significantly larger context than we typically could and still have it retain that larger context. So that's really all we have to do here. And if you just want to try out the wider context for yourself, feel free to pull down Wizard LM, the blue quantized, and that will be in the description below. But that's it. If this is helpful, please like and subscribe, and please let us know in the comments what you'd like to hear about next. And tune in next time when we're going to be talking about how could we possibly adapt landmark attention to allow us more dynamic control over our context. See y'all next time.